amplitudes.
Thank you so much. Well, good morning, everyone, and thank you so much to the organizers for the possibility to share my research today with you. I'm not strictly working with integrability, but I'm trying to find the interplay between bootstrap techniques in AdS CFT and integrability, so I'm going to try to report on some exact results for string amplitudes in AdS. So it's going to be a summary of some papers with, is this on? Okay, with Fernando Aldaime, supervisor in Oxford, Tobias Hansen, Aurélie Sangaré, Clément Virali, and Shinanzu. So I'll start by trying to motivate why string amplitudes are interested in AdS. And immediately after that, I will focus on the high energy limits and what we can learn about them. This will lead us to present building blocks of AdS string amplitudes in AdS. But this is going to be just the last part of the talk because it's a bit more technical and mathematical. So I'm just going to focus on the high energy limits, and in particular on the Regge limit, where the interplay with integrability is more evident. And I'll conclude with some key takeaways and future directions. OK, so very basically, we're going to study scattering amplitudes. They are basic objects lying at the interface between particle physics, mathematics, and string theory, and more. And they are predictive tools, giving us the probability for a certain process to happen. But for us, they will especially be important because they allow us to uncover structure and behavioral symmetries that may not be evident from a Lagrangian formulation. Today, we're going to focus on string scattering amplitudes in flat space. So in flat space, we have a well-established setup, which is the perturbative string theory. And in principle, we have worksheet methods that allow us to study any amplitude as a sum over topologies, namely puncture Riemann surfaces of increasing genus with insertions of vertex operators that corresponds to your initial and final states. So very schematically here, what we have is an integral like the metrics and the fields, as usual in path integral formulations. And importantly, we have this sum over topologies. So for tree level, which is the topic of today's talk, we're going to have a Riemann surface with insertions of vertex operators of these states lambda I. And then we're going to expand in powers of the string coupling constant. So we're going to take it small to consider weakly coupled strings. Essentially, we have two parameters, GS, which is the string coupling constant, set to 0, and then alpha prime, which is going to be very important. And it gives you a sense of the size of the string. So we have to think that as alpha prime is tuned to 0, for example, this is the point particle limit. And then we take alpha prime corrections or equivalently stringy corrections. We're going to investigate, for example, the alpha prime to infinity limit, which is the very stringy or high energy behavior and something in between. An important point, even just in flat space, is that sometimes this sum is dominated by a saddle point, allowing us to make exact computations. And we're going to be back to this even in AdS. Now, an outstanding question is, what about curved spacetimes? And if you take any standard formulation from flat space and try to extend this to a general curved background, it's very difficult to do so. And at the moment, even if in principle there is a perturbative genus expansion, there is no direct worksheet approach available, even at tree level. So we need to make progress somehow. In our favor, we have AdS CFT, which allows us to describe string scattering amplitudes in AdS from CFT correlation functions of the boundary theory, where we can use the beautiful setup of CFT techniques and so on. We also have exact limits that can teach us a lot about the more complicated theory in AdS. First of all, we have the flat space limit, which is going to be our starting point to develop the theory in AdS. But we also have high energy limits where computations can be done exactly. So we do need additional tools to make progress in this setup. We want to study amplitudes of strings in AdS. The main context is going to be AdS CFT, but there is so much more helping us to make progress. So we're going to use a bootstrap approach. But as I was saying, we're going to focus on flat space limits and high energy limits and what we can learn and infer about the worksheet structure of AdS. And integrability definitely has a role here, giving us information about the polar structure of the amplitude, as I was going to try to explain. But even number theory, from a mathematical point of view, is going to be fundamental here, because it is going to be the right language to describe the structure of strings in AdS. So lesson to learn. Studying tractable limits, such as flat space or high energy, will help us build intuition for the full theory. So let's start. We focus on the paradigmatic example of AdS5 cross S5, dual 2 for D n equals 4 super Mills. And even in the presence of a maximally supersymmetric setup, alpha prime corrections, so stringy corrections, are very challenging to compute. And the Virasoro-Shapiro program in AdS was born a couple of years ago with Fernando, Tobias Hansen, and João Silva, and with the aim of learning how to analyze and including curvature corrections in AdS. The main object of study is the scattering of 4 gravitons at 3 level, so we have a Riemann surface with 4 punctures. In flat space, this is the very well-known Virasoro-Shapiro amplitude. It's one of the outstanding results in string theory. And even if it was not the original form, now we know that it can be written as a worksheet integral of this kind, where Z is the cross ratio on the sphere after you use conformal invariance to fix 3 points. As we go to AdS5 cross S5, we don't know how to quantize perturbative string theory on this setup, but we do have a DSCFT, which tells us that this is the correlator of 4 stress tensor multiplets to leading order in a large central charge expansion. And here, S, T, and U are the Mandelstam variables, so the kinematic invariance of your strings. If you carry out this worksheet integral, you get the very beautiful and neat ratio of gamma function here, but maybe a less appreciated representation, here's the following, which is very illuminating because it tells us about the structure of the amplitude, mathematically speaking. And to be precise, you can notice that as you expand the amplitude, you're going to get some very special numbers, which are called zeta values. And I will define them in a minute. But not just zeta values, you get odd zeta values. And these are the ones which are single-valued. This maps to the single-valued nature of this worksheet integral. Indeed, if you look at the integrand, it is single-valued as you move around the puncture on the worksheet. So single-valued is something which is evident in flat space, and we're going to stick to that. More specifically, if you do the low-energy expansion, so alpha prime to 0, I said before that alpha prime is the size of the string, so alpha prime to 0 is really the point particle limit, so no surprise that this is a supergravity result. But then we have an infinite tower of stringy corrections. So these Wilson coefficient alpha, they live in the ring of single-valued zeta values, and this is very deep. The idea of Fernando, Tobias, and João was to assume that this is also the case for AdS corrections. So it is a conjecture, but we're going to see that we have a lot of evidence for that. And this led to a precise proposal for the structure of the amplitude in AdS5 cross S5, which is the following. First of all, the amplitude in AdS is defined as an expansion around flat space. So we are expanding in alpha prime over R squared, where R is the radius of AdS, and we include perturbatively in 1 over R, the curvature corrections. And at each order, the correction take the form of a genus 0 worksheet integral, exactly as in flat space, but now with insertions of a weight 3K single-valued multi-polylog. So these W are just the insertions of polylogs. I'm going to define them in the next slide. And this provides an algorithm that allows us to compute each AdS correction modulo input from integrability. And what this means is that while for the first curvature correction, it is enough to impose single-valuedness, the structure of poles, and so on, to fix it completely in a bootstrap setup, starting already from the second correction, we need input and help from integrability. For example, giving us like the dimensions of Konishi-like operators will fix the structure of the poles. So let's very briefly present the building blocks of these ansatz. We have a multiple polylog. This is labeled by word W with letters in some alphabet, and the length of the word is called weight. These are recursively defined by these differential equations and these boundary conditions, where E is the empty word, and then we have an alphabet of letters forming the word W. So as an example, for example, if you have all zeros as the letter, this will reproduce for you the powers of logs, while less trivial example, if you have a strings of 0 and the 1, this is just the classical polylogs, and then you have much more. So to sum up, these are just analytic functions of a single complex variable, which are multi-valued on the complex plane. So you will have branch cut at 0 and or 1. What we can do is to consider linear combinations of polylogs, such that all the branch cuts cancel, and these are going to be our single-value multi-polylogs. So we act with a single-value map on the multi-valued one, and it will return to us the single-valued one, wherever that is. A very simple example, the log of z, of course, is multi-valued on the complex plane, but you can just add the log of z bar, and it will give you a single-valued extension to that. But this can be done more generally for any multiple polylog, and by now we know the perfect classification to any weight, thanks to Francis Brown. An important lesson here is that at any given weight, there is a finite dimensional vector space of available functions, which makes them very interesting in terms of an ansatz, of course. And the very last piece of information that we're going to need for today is that zeta values can be defined as multiple polylogs at 1. So this is precisely the sense that I was mentioning before, such that like the zeta values at odd integers are the ones which are single-valued, because if you try to make the same for even integers, they'll just vanish. So it's highly non-trivial. And this also motivates this structure, because the multiple polylogs, the single-valued ones, are the right functions, such that upon integration over the Riemann sphere, they will return to you the single-valued zeta values, exactly as in flat space. So single-valuedness is our guiding principle and our key assumption here. So now we have two questions. On one side, we would like to determine the amplitude in AdS to all orders in 1 over R. On the other side, we would like to make connections to more direct worksheet computations, which is what is lacking in AdS. And turns out that the strategy to reply to both these answers simultaneously is to focus on more accessible limits, and in particular to the high energy limits, which provide a lot of insights into the full theory. So let's start. First, we investigated the high energy limit. In this limit, I take S and T, the Mandelstam variable, to be large, and keep S over T fixed, the scattering amplitude. We have a dual perspective. On one side, we could take the point of view from space-time. Already in flat space, back to the 80s, Gross and Mende had this beautiful result about strings in high energy limit. And we know that the path integral is dominated by a classical solution, which is the following. And importantly, it is single-valued on the worksheet. What we did in this paper with Fernando and Tobias is to extend this to AdS by proposing a classical scattering problem in AdS, a bosonic model actually, and we proposed an algorithm to solve the equation of motions in 1 over R to any order in 1 over R. And the solution takes this form, where L are just linear combination of single-value multipolylogs. So again, they are the right building blocks of the answer. But we also have the worksheet point of view. In flat space, if we go back to the worksheet integral, so here, if S and T are large, we can just do a saddle point approximation, and the saddle point is S over S plus T. But most interestingly, even for the full AdS Virasoro-Shapiro amplitude, each curvature correction is just a rational function in S and T, so it cannot modify the location of the pole in a 1 over R expansion. So we are done, because we have it from flat space, so this the result in flat space. The answer in AdS is just going to be the same thing times the integrand evaluated on the saddle point. And by requiring that the two predictions agree, we find this very nice and compact result. So curvature corrections exponentiate to each order in S squared over R squared fixed. And the key point is that only the subleading correction is relevant in this limit, and it's really all we have to say. And I just wanted to mention that the same structure of multiple polylogs turns out to be the case for other backgrounds in AdS, as Shai will review. And this high energy limit is found to be exactly the case even in those backgrounds. So it's highly non-trivial. Then we investigated the richer limit, which is the Regge limit. So T is still large, but S is finite. And what we found with Fernando, Cleman, and Shinan is that to all orders, the amplitude can be written as derivative of the flat space Regge limit. And this is really the interplay with integrability, because we all know that the big achievement of Regge theory is that you need only the leading trajectory in cubic couplings to fix the entire amplitude. But here, these operators are the Konishi-like operators, which are a target of integrability. So what we did is to write the AdS Virasoro-Shapiro amplitude in the Regge limit just in terms of the CFT data of these exchange operators. So the OPE coefficients, and these are related to dimensions of these operators in n equals 4 Super-Yang-Mills at strong coupling. And this operator R is the effect of the curvature of the background, is a differential operator, so its derivatives with respect to the spin J. And in 1 over R, we have a way to fix it to any order because it satisfies a difference equation. And as you can see, derivatives with respect to J will eventually eat T to the J, which is the flat space result in the Regge limit, producing powers of logs. So we're always going to have logarithmic corrections in T, and this reflects the fact that in AdS, perturbatively in 1 over R, you have higher order poles. So what we can do now? We can infer some results that are exact, again, 1 over r. First, we can resum all the leading logs, and leading logs exponentiate, matching the high energy result in the right regime. But we can do more. We can resum the subleading logs. And this is extremely simple with respect to the other computations. And moreover, it provides an all-order results in the limit of large RT with log cube t over r squared fixed. So again, this is a regime where exact computations can be done. We can do even more. And now that we have the Regge limit from these derivatives of flat space perspective, we can try to understand what this implies for the worldsheet and how can we go back to the full theory. So first, knowing the Regge limit in AdS, we can ask ourselves what is the manipulation that we need to do to the integrand such that it reproduces the Regge limit. And this is the right limit to engineer. We send t to infinity, z to 0, while keeping t times z fixed. So this is going to be the worldsheet integrand in the Regge limit that reproduces the right Regge limit. And indeed, it matches perfectly with the prediction. But we can do even more, and now reverse our logic and look for the right integrand without knowing what was the proposal. So I told you that the proposal for the full amplitude is in terms of single value multipolylogs, but let's forget about that and just ask ourselves, what is the right integrand that we need to put to reproduce the right Regge limit, which is derivatives of the flat space answer? And since we have derivatives with respect to j, we need to insert a function which is expanded in powers of logs of modulus of z. Indeed, if you imagine to just put log of modulus of z here, this is just derivative with respect to j of this factor, right? So we need to do that. And what this implies beautifully is this functional equation for the right insertion in the Regge limit. That's our prediction from the other computation that I showed. And again, this is known to any order in 1 over r. So this fixes families of solution for the worldsheet integral to all orders in the curvature expansion. This is deep, lastly, for the reason that this is a single-valued log. So it is manifestly single-valued around 0, which is a nice confirmation, if you wish, of the full ansatz. And the single-value log is the symptotic of single-value multipolylogs, so we have a nice independent check of the full answer. So lesson to learn from this second part is that the high energy limits are a natural step toward an AdS worldsheet theory, enabling us to probe the theory's mathematical structure across different regimes. And driven by this, now we're going to propose a mathematical structure of the AdS string amplitudes. Can I ask you how much time I have left? OK, perfect. So as usual, we start from flat space, which is our starting point, but also like inspiration for methods in AdS. And now we forget about the specific theory, and we just want to extract the building blocks, mathematically speaking. It's a bit abstract, but I think really nice. So for closed strings, we have this function, which is called complex beta function. And it's exactly the same as like Virasoro-Shapiro amplitude, but without the 1 over u squared factor. So now we are really not thinking about the theory. And this evaluates to the ratio of gamma function. Similarly, now we can extend to open strings. And open strings are now given by the other beta function, which is now a one-dimensional integral from 0 to 1, giving another ratio of gamma function. And this would map to the Veneziano amplitude, for example. One of the most beautiful and significant relations of Euler and complex beta functions are that they are related by a single-valued map, very much like the single-valued map between polylogs and single-valued polylogs. So we can think of the complex beta, or equivalently the closed string case, as the single-valued map of the open string amplitude. And if you want, this can be rephrased in terms of the KLT relations. So back to the 80s, this very nice relation were proposed about the relation between perturbative closed string amplitudes at tree level and bilinears of open string amplitudes. So the square of the beta function gives you the complex beta function up to this kernel. And this kernel is not just a random function, of course. It's very non-trivial that it exists at all, because you have to think that you want to reproduce like a physical answer on the left-hand side. So this kernel needs to cancel all the spurious poles and gives the right zeros. So this is really amazing that it exists, even in flat space. Yeah.
There has to be some function, right? Because if you're writing a function s and t equals another function
Mm-hmm.
So I guess, like, what are the special properties of that kernel which make it more interesting than just been random?
Yeah. Well, as I was saying, like, for example, if you have Young-Mills that squares, like Young-Mills and gravity, they have very different poles. But for example, if you have double poles on one side, then the kernel needs to cancel exactly the double pole.
Didn't there have to be a kernel by construction? I mean, you're relating two functions. Like any two functions are related by a third function, right?
Yeah, of course.
So I guess, like, so why is it so surprising that such a relation exists?
I guess, I mean, you don't know what's the double copy, right? You take any single copy theories, and you don't know what to expect. But there is one function which gives you gravity, and it's universal, moreover, right? If you change the single copy, it's still the same function. So it is special, I think. Thanks. So motivated by what I explained before, now the proposal is that the building blocks of AdS string amplitudes are the same kind of worksheet integrals, so generalization of Euler and complex beta function, with insertions now of polylogs. Single value multipolylogs for closed strings, and multiple polylogs for open strings. So what we are looking for is now a single value map, or a KLT kind of relation, between this generalization of Euler and complex beta function. So if you want, we are looking for something like this. And this is, I think, the most technical slide of the talk. But as usual, we need to pick the right language to get a nice answer. And the right language in this setup is to study the generating functions. So if you want, like we're used to this in physics and maths, but for example, for multiple polylogs, you can put them all together in a generating function that, as you expand in something, will give you the multiple polylog at any weight. And here, the expansion is in E0 and 1. They are two non-commutative variables that are associated with the letter 0, 1 of the alphabet that I was introducing before. So you do this kind of game for the building blocks of AdS open and closed string amplitudes. So curly J and curly I are the generating function of our building blocks. So at each order in E0 and E1, you pick J or I, and this is the proposal for that weight. So what we are after is a KLT relation between the generating function, because this encapsulates all the weights. And the kernel itself, of course, by construction, is going to be an expansion in the non-commutative variables. What we find, quite remarkably, I think, is that the kernel, even in AdS, takes a very simple and elegant form, which is the following. M0 and M1 are the monodromy matrices found by Francis Brown, governing the discontinuities of multiple polylogs as we cross the real line. And more explicitly, if you wish, to all orders, we find that this is the inverse of the kernel in AdS, to each order in E0 and 1. It's a bit technical, but if people are familiar with KLT relations, it's also the case in flat space that the inverse of the kernel is even more interesting, because it is related to physical amplitudes. So not only it's an interesting function, but if you study the inverse of the kernel, it encapsulates the information about scattering of cubic, scalars, and so on. Turns out that even if we don't understand it yet, even in AdS, the inverse of the kernel is a very beautiful and compact formal, which is much easier to deal with. And it takes this form. So we have cotangent pi s plus E0, so shift by E0 and shift by E1, but we have this non-trivial like multiplication by z that I didn't introduce, but it's just generating functions of multiple zeta values. So if you want the same generating functions of polylogs, but at 1. And as you expand in E0 E1, this reproduces exactly the inverse of the kernel in flat space. So if you go back to this, the inverse of that is the cotangent. So it's exactly that, but this is an all-ordered prediction. So at each order in E0 E1, it will give you the right kernel in AdS. Of course, a lot remains to understand about this. I think I will conclude by giving you some key takeaways and leaving you with future directions. So I try to present some results about this program of how to compute string amplitudes in AdS from alternative tools. We said there is no worksheet theory that, and we need to make progress somehow. So AdS-CFT definitely helps, but we need a lot of help from integrability, number theory, and exact limits. So first, the single valuedness has a central role here, exactly as in flat space, but we don't understand it. So flat space is an evidence, but I think even more in AdS, it's a guiding principle. Turns out to be correct because all the predictions match perfectly with integrability and localization results, but a lot remains to be understood. Also, we can do exact computations in the energy limits, and they give us insights on the full theory and the nice interplay with integrability. This led us to uncover the mathematical structure of string amplitudes in AdS. We just started looking at that and trying to extend the beautiful relations in flat space to AdS, which was not done at the level of the string theory yet. And as some future directions, some of them are really beyond my area of expertise, but I leave them there. First, it would be nice to try to understand to which extent we can combine, for example, the energy results with integrability and the structure of the solution to go to higher orders in 1/R. See if there are nice patterns, now that we also know how to do the integrals themselves. And definitely we need to understand more about these KLT relations, like to focus on specific amplitudes and try to see what's there. Of course, the ultimate goal would be to find the direct string theory computation that would map and match our results, hopefully, but this is still open. And maybe I'll leave you there with, it would be amazing to develop a quantum spectral cut for the DS-Virasoro-Shapiro amplitude and really try to exploit the nice interplay with integrability. With this, I will thank you for your attention.
Well, amazingly, we're back on schedule, right? I mean, you were even a bit too quick. So we have time for questions.
Could you explain again maybe what it exactly means to compute an open string amplitude on AdS5 times S5? I mean, you're not doing type 1 string.
No, of course. So here, I'm not referring to AdS5 cross S5. The last piece was really just AdS in general, like a background in AdS. Of course, for open strings, you need a different background, like AdS5 cross S3, and like you need to do some supersymmetry. I think maybe Shai will mention something later, but here I was just really saying that motivated by the results for the open and closed strings in AdS, we proposed that this would be the general structure in AdS. Of course, then to do specific amplitudes, you need to specify the right background in AdS, the right compact space, and so on.
So this statement about the kernel is just a statement about function spaces that I can compose.
Yeah, definitely, 100%. Then it's still work in progress. Focusing on specific amplitudes seems very non-trivial to get it there.
Thanks.
More questions?
Hi, Maria. Thank you for your very nice talk. I have a question about high-energy limit. Have you considered construct the vertex operator in this high-energy limit?
We have not.
Already have this.
So for this case, like the details about vertex operators are subleading in this limit. So you don't really need to know them exactly, but people are working on vertex operator, even like at finite SNT. It's highly non-trivial in AdS5 cross S5.
Thank you.
Thanks.
Agadi?
So some of your assumptions are kind of may not be specific to AdS5 S5. For example, signal validness. Do you think if you consider just string theory in asymptotically flat space, you should get similar?
Sorry?
If you consider string theory in asymptotically flat space, bosonic string theory, and compute for graviton scattering,
like with single valuedness.
curvature expansion, would you think you should get similar single validness property?
I don't know. This is really like inspired by the fact that for closed strings in flat space, you have these asymptotics which contain single valued zetas. So now if you look at the worksheet, you need to have polylogs to get them.
Maybe it may be actually true that if you...
Maybe, yeah.
It may be generic fact.
I don't know actually.
Yeah.
It could be the case, yeah. It is really a conjecture, like a driving assumption. It turns out to be there, but at least from my perspective, we don't understand the physics of that. So I don't know how this is specific to AdS versus asymptotically flat space.
Can I ask one little point? If you just bring up your final inverse kernel.
Yeah.
So what's blue and what's not blue in that formula?
So this is I just wanted to make the comparison with flat space.
Right.
So here,
You said these are the bits which are not in flat space. Okay, I get it.
yeah, that's flat space, and then that's how to uplift.
My misunderstanding. Thanks. Do we have other questions? Then let's thank you again for this nice talk.
Thanks.